Buongiorno a tutti, sono Cristian Gaudino di Engine Soft. Vi ringrazio di aver partecipato oggi a questo webinar sul design food processing equipment. Avremo modo di vedere durante questo webinar molti esempi utilizzati, molti esempi fatti con Rocky, con clienti reali, e avremo modo di fare una bella overview anche sul prodotto Rocky. Quindi in questo momento, per non dilungarci troppo con chiacchiere, darei subito la parola al collega Ahmad, che ci fa questa bella presentazione direttamente dal Brasile, dalla casa madre di Rocky. Quindi lascerei a lui la parola. La presentazione durerà circa 30 minuti, dopodiché ci sarà la possibilità di fare domande. Potete scriverla nella chat o farla direttamente a voce. Ahmad, se ci sarà il tempo sufficiente, risponderà a tutti, e così almeno avremo le possibilità di chiarire eventuali dubbi. Teniamoci in contatto anche dopo. Chi ha bisogno di informazioni saremo a vostra disposizione. Quindi do la parola ad Ahmad e quindi switchiamo in inglese. Ahmad, it's your turn, so I give you the floor, and thank you for making the presentation.
Thank you very much. Thanks. Hi, everyone, and thank you for joining us. I'm Ahmad, Application Engineer at ESSS in Rocky Business Unit, and today we will discuss how to use Rocky DEM to improve design of food processing equipments and to evaluate the parameters affecting these processes. We will begin this session presenting what are the main challenges in designing industrial food processing equipments. Then we will proceed to know what's the particle simulation and the areas it can be used for equipment design, specifically in food processing equipments. And later on, we will discuss a couple of examples and case studies in detail to see how Rocky previously was used to solve the challenging problems in these processes. Most of these challenges are same between different variable industries. So we just look at the key factors and we use the same factors to simulate different processes. Let's look at some examples of equipment widely used in industries that are relied on the transport of particles. For example, for the transport of usually dried material, we're using conveying systems. For example, using chevron belt for the potato transfer on the conveyors. And also we have mixings that are widely used for early to final stage of the final product. And also we have seasoning and granulation and crushers involved in the efficient treatment of the material that need to be assessed carefully. And packaging, where the final product are stored efficiently with minimum damage in a desired form of the packages for final product. There are common challenges and concerns in process equipment shared between most industries, such as optimizing process capacity and efficiency, analyzing equipment life and minimizing wear on the equipment, eliminating the particle degradation through optimized handling. And overcoming these problems is hugely relied on the first step of manufacturing, which is equipment design. As it's expected to create a reliable and efficient process, design decision is crucial, as almost 70% of the costs are committed at this stage, while at the same time, at the design process, we only have 10% of the total cost spent. In a way of overcoming these challenges, we have several tools ahead of us. For sure, we have experiments and real life observation. And beside that, we have simulation of those realities for parametric analysis. Talking about computational tools and computing in process design, it's important for us to consider that modeling as a tool should be used as a tool that supplements theory and experiments, and it should not be viewed as a substitute for real work. So it serves to complement and to provide additional insight that are often impractical or impossible to discover through real world. So any industry that embraces simulations methods results in huge saving for them in cost and time in getting products to the market. Here I'm going to show a different, very broad application of the particle simulation. Particle simulation is useful when we need to get insight into the behavior of bulk material. And we can apply this solution to a wide range of industries that include particulate matter such as food and drug industry, agricultural industry, and so on. The most popular method for particle simulation is discrete element method, or briefly DEM. A DEM solver tracks particle motion by solving equations like Newton's second law that represent their rotation and translational movements. For example, here on left, we have barley conveyor that processes the wet and sticky agricultural material. We can see how the selection of the particle material and adhesiveness of the material affect the movement of them. In the center, we see tablet coater and how post-processing tools can be used to visualize the state of the mixing and residence time of the particles. And on the right-hand side, we have the bucket conveyor, and we can see how the geometry movement and particle geometry interaction can be important in DEM simulation to be able to represent real shape of the particle, movement of the geometry, and have motion, different motion frames nested together. Rocky DEM is a leading software in DEM simulation that allows multi-GPU processing for problems with millions of particles. And also it allows real particle-shaped representation for complex problems. And in addition, it gives option features like breakage and wear models that, with, for example, breakage of particles represent real process accurately. And also is fully integrated with ANSYS software for cases with fluid or structure interaction. Rocky, we can simulate particles with their real shape. For example, we have gummy bears, then we have chips, and after that we have, let's say, noodle that is fiber material. So you can see each of them are different shapes, different based on the real representation. So with this, we can define variety of shapes from a custom designed STL file to Rocky. And this implies a real representation and higher accuracy of the simulation as we use the real shape of the material for our simulations. As an example, here we have fiber particles. We can see how the hay fibers are getting compressed. And this is actually a good example of a calibration of the material, which comes after comparing the experiment result with simulated ones. Here, specifically, we compare and analyze the compression force versus displacement during this compression. And with that, we can calibrate the parameters that we need for the simulation. But just a broader view over this, we just want to represent how like custom fibers that are 1D particles are represented in a simulation. The other feature I want to talk about is that Rocky allows you to configure complex geometry movements by enabling as many translational, rotational, and free body motions and absolutely nested combinations of them. So whether you want to prescribe exact movement or have the geometry components move freely in response to outside force like particle hitting them or as a result of the gravity force the geometry moves, Rocky can handle all those without any coupling, and all of this can be done natively in Rocky with native movement tools. For example, we have a pan mixer on the right side with nested movement of the body parts that is used for the mixing of the powder. The other feature is breakage model that captures size-dependent fragments and is based on the accumulation of the energy due to the impacts. In here, we can see the free body motion of the cone crusher. So the cone has free body motion, and as a result of the particles hitting that cone, it starts to rotate. Also, the breakage model that preserves the volume and mass of the particles as they crushed by the cone crusher. All these models, again, are Rocky native features that do not need to use another third-party software to be coupled to Rocky. All of them can be done in Rocky. Another breakage model that can be imposed on particles with shapes, as we can see here, we have the breakage of the chip material. And Rocky can also utilize multi-GPU to remove the bottleneck from simulation with large number of calculations. This is helpful because it allows us to run the simulation faster and to handle cases closer to real condition without any scaling. For example, in here we have the tablet coater simulated by BMS as real scale that includes more than 100 million contact faces between particles. It's important to pay attention to the shape of the tablet as well, as each of them are simulated with their exact shape. So using multiple GPU, we can stack them next to each other, and it enables us to simulate huge simulations like what we can see here. And also Rocky, as I said, is fully integrated with ANSYS tools, such as Space Claim to optimize the topology and geometry of the equipments, and Fluent, for example, to model the fluid flow and the transfer of the moment and heat between the fluid and particle phases. And also ANSYS mechanical can be coupled with Rocky for the static and transient evolution of the loads, deformation, and stresses on the equipment bolts. And combine them all together, we have Design Explorer coupling with Rocky that enable us to parameterize the process parameters and helps us to achieve the optimization objectives. And all of this can be done in ANSYS Workbench. So we just have Rocky as one block in addition to other blocks available in ANSYS Workbench. For example, if I want to talk about DEM and CFD, CFD stands for computational fluid dynamic coupling, we can see examples here. So this coupling is through the transfer of fluid forces to the particle and vice versa, depending on the selected coupling schemes. These forces then will be used next to DEM forces to determine the movement of the particles using the Newton's second law. For example, on the left side, we can see how the particle movement are different based on their material and shape. Lighter material like paper are moving with airflow, but heavier ones like rocks are falling down. And on the right side, we can see fluidized bed, which is a common application of two-way coupled between DEM and CFD in oil and gas sector. After this brief overview of some of the major features in Rocky, I'm going to move forward to a set of real simulation examples in food industry and case studies in the same industry. These examples are applicable to different industries as well at different stages of the process, from mixing and material handling to packaging and end product quality control. Talking about mixing and blending processes, different structure and design can be easily represented and simulated in Rocky. For example, in the first example on the left, we can see the diffusive mixing process like V-Blender, where using post-processing tools allows us to see the effect of loading procedure on the homogeneous distribution of the product. Comparing different loading methods, we can see which one gives us more uniform distribution of the material. On the second video on the right side, show the hand mixing of nuts. And as the mixing proceeds, we can find the time it takes for the process to reach the stage of complete mixing. And so based on this knowledge, we can change the design and optimize the design of the process that we have. Here it was a simple process for hand mixing, but it can be more complex real industrial processes. The important parameter in mixing drum is to decrease the time for the system to reach the stage of complete mixing. This time is important in food and chemical industries because we want to prevent the product degradation. And using rocky post-processing tools, we can convert discrete variable to continuous form of them. For example, to see the mass fraction and volume fraction inside the drum. And by taking a sample, we can determine the degree of mixing. Using a statistical approach, we can determine parameters like lazy mixing index to find the time the process has reached the complete mixing. For example, here, as the lazy mixing index is getting closer to 1, we have a binary mixture of particles with homogeneous distribution. So when the lazy mixing index reach 1, we just need to find the time, and we know at this time the mixing system has reached complete homogeneous distribution. And for example, one optimization study is that to speed up the mixing time under the same load of material, we can increase the rotor speed. However, at the same time, we prefer to have an energy efficient process that can work under the maximum load of particles. These are all parameters that can be fed to software as objective of the optimization set that will help the process designer to be able to have a clear decision over the operating conditions. Moving on with other example of a situation where the particles are colliding frequently with each other in the process, the quality control becomes important. For example, in pharma sector, minimizing tablet edge chipping is important as it will assure the manufacturer to determine optimal product quality based on end product shape and design parameters. With models like collision statistics, we can obtain average tangential stresses on the particle that give us deeper knowledge of the process behavior. We can see the edges of the tablet here that are more prone to be chipped as a result of higher impact during the process at these regions. The same simulation can be applied to any drying and mixing process in the food industry to make sure we do not damage the end product. In the next case, we see how Rocky simulation has enabled PepsiCo to improve the accuracy of their factory equipment setup. The simulation enabled them to reduce the number of adjustments required and help them identify potential custom modification for higher efficiency and cost reduction. Seasoning procedure of chips and optimized rotation speed are some of many parameters that can be optimized to achieve higher efficiency here. Also, quality control examples can be applied to this kind of simulation to assure not to induce too much stress on the dried food material that would cause their breakage. Next, I'm going to show an example of process that involves heat exchange between the particle and equipment valves. Here we have conical dryer that fills up with particle, and in the next step, these particles gain heat through conductive heat transfer, and then cool down as they are in touch with walls and finally discharge from the process. It's important to see how the whole process is defined in a single project. This enables us to run optimization tools between different stages of the process from filling to discharge. These optimization sets can be to increase the efficiency and to minimize the operating time of the process. Next example, again, we have the heat exchange problem in a multi-physics framework. So here we have DEM coupled with CFD to evaluate both conductive and convective heat transfer between the coffee beans and the fluid flow. The design explore optimization on the rotation speed and inlet airflow temperature all effective to determine and minimize the hot spots in the process and to increase the uniformity of the drying. On the left video, we can see the particle movement coming from the DEM simulation, and on the right side, we can see velocity, temperature and temperature profile gathered from a CFD calculation. And the coupling between these two enables us to do the multi-physics simulation simply all together in Rocky. In the next example, we see chevron belt and how the material selection and belt design can be imposed in the simulation, Rocky DEM, and in further steps can be optimized to get optimum design of our chevron belt, and how the arrangement of this belt should be all together to make sure we have a continuous movements of the material here, for example, are working on potatoes. On the second video, we can see the hopper discharge simulation and its flow pattern with the goal to minimize the stagnant zones. Here we can see how the change in feather design has resulted in uniform drawdown from the hopper. In the first part of the video, we use the post-processing tools to find the stagnant zone and found the probable cause of them. And the second part, we modify the feather design with added rectangular duct. So we observe how it helps us to have the flowability of the particles in the hopper. And here we have other example of controlling discharge in vertical filling and how the loading and loading the material can be optimized to prevent arching at the discharge. And clearly simulation give a higher level of insight into parameters that can be modified to reach the desired outcome. Another important sector that's dealing with particulate matter is sorting and separation. Here on the left side, we have the tumbler screening machine, and where the fed materials with different size are separated. And on the right-hand side, we have the bowl sorting, where the design assures the correct orientation of the particle as they leave the sorting machine. So we want to make sure all the leaving products are facing upward with the hole on top. And that's how the real shape of the particles helps us to be able to run the simulation and make sure the design that we have allows us to be able to sort the product in a way that we want. And then we can imply the same thing in real world and see if so combining the simulation and the experiments all together, it helps us to get to the point that we want to the end product as fast as possible. And the important thing again is to remember how all these simulations are made through real shape representation of the particle, combined with the comprehensive motion frames that all can be applied natively in Rocky. In the continuation of the case study by PepsiCo that we saw before, we can point out to how Rocky was used to packaging processes to achieve optimum load of product based on the volume filled. Also, using real shape of the material allows us to perform virtual experiments on product lines and simulate the board in real life with true physical representation of them. We can see the part is going in the package, and based on the volume it takes, we can have the optimum amount of material in the desired shape and design of the packages. With that, I want to conclude our webinar for today. One thing to remember from this brief talk is to understand that a lot of hidden alternatives exist at each level of design, that each of them can be hugely beneficial to the production line. Rocky as a simulation tool can be used for complex simulation of particle that stands beside advanced post-processing and optimization tools to help gaining deeper insight into the problem. I hope you were able to find this webinar helpful. In case you have a specific question or request, please find us through our direct office or channel partner. Once again, I want to thank EngineSoft for arranging this webinar, and thank you all for attending this webinar. Thanks.
Thank you, Ahmad. If there is some question for Ahmad about the Rocky simulation, Ahmad can answer for you, and so we can give some minutes for question if there are some questions. So now I believe all of you have the microphone open. So if you want to make some questions, please make it, or otherwise write in the chat. There is a question in the chat. You can look, Ahmad, the question on the chat.
I cannot see on the chat. I cannot see the question. Can you please read that for me? Because I do not see it here.
I'm writing.
Yep. I see one question like the difference between multi-GPU, GPU, and CPU. So there is a common question actually that when should we use CPU, when should we use GPU, and when we should go like all the way in and invest a lot and use multi-GPU. So usually for small problems like less than 1 million particles with spherical particles, these are easy calculations. Not really easy, but I'm saying like it's easier than when we have shaped particles with like billions of particles. In this situation, CPU is better to be used, and the cost is much more efficient, and the timing is not going to be that much improved. When we use like shaped particles and when we have more amount of particles that need to be calculated, then at that time we need to move GPU, we need to consider GPUs. And when we have a large amount of particles, like 10 million particles, then using one GPU restricts us to the memory that one GPU presents. So to calculate 10 million particles, we need more memories. The only possible solution is to use multi-GPUs. So again, CPU for smaller simulations, something medium-sized GPU is good, something that is huge number of particles with shape representation, then it needs multi-GPU. And again, Rocky enables us to, this is actually one of the features in Rocky that make it stand in the market to be able to work with multiple GPUs and be able to simulate huge and industrial scale problems. Okay, we do not have any other question. Again, if you guys have any questions, please feel free to reach us through EngineSoft or our direct offices. You can see the website, and through website you can contact us. Thank you very much.
Okay, thank you, Ahmad. Thank you to all the participants. For any information, you have my email and our contact, so we can ask you any other future questions, or we can have a future meeting for explore more in detail this information. Let us know, and we are available for that. So thank you very much, Ahmad. Thank you very much all in AAA. Thank you very much all the participants. See you soon. Bye-bye.